Well, thanks a lot. Thanks for the invitation and for going forward with the meeting. And well, life is life. So what can we do? 2 years ago also I was here. It was my last meeting. That's not my first meeting though, but one of the first ones. And I hope there will be many more. I'm gonna talk today about the work done in collaboration with Alex Jenkins, who is now a postdoc in UCL. And it's based on an idea that is relatively simple, but more powerful than what we expected. And the idea is kind of represented by this picture, where we have tried to make an artistic impression. Artistic means us, so we didn't have any budget for artists yet. So we put a binary system orbiting, okay, in principle, isolated from any other gravitational source in the universe, but then there is a gravitational wave background. It could be a single wave, it doesn't matter, but as I'm going to explain, it's better that it's a background which has a wide spectrum of gravitational waves going through, and then it's a classical result of Misner, Wheeler, Thorne, or even before, that the gravitational wave is going to modify the orbital motion of these guys. Of course, if it's just transient, it's going to be something that is hard to observe. But if it is happening all the time, like in these stochastic backgrounds, and if the frequency of this wave, you can see already, if you are kind of in resonance with the wave length of this guy, it may accumulate over time and eventually destroy the binary or do something to the binary that you can see. Right, so that's the explanation of the title. So first, just to put everyone on the same page on gravity waves and the ones I'm going to discuss. So there is this little way, this simple way of classifying gravitational waves. So they can be either transient or persistent, so something that just bursts in the universe, or a kind of binary that is orbiting for a long time, and it generates a very nicely phase coherent signal. It can be also phase model or phase model, meaning that this corresponds to a kind of harmonic or close to harmonic system with a particular frequency there. The opposite one in the transient is an explosion with a mass flying around all over the place, and then you see it is harder to, there is more than one phase in this signal. This is, by the way, time, and this is amplitude. And finally, there is the place where there are waves all the time. They have all the phases, they are coherent, and this is the kind of background that I'm going to be mostly discussing, right? Because the binary system, as I said, is a good detector of gravity waves if you are in resonance. So you can imagine that for this kind of signal, it could be great, but you have to be very close to resonance. We don't know yet how close to resonance we have to be. This is something we have to do. But for now, we assume that there is a whole spectrum of gravity waves and see what happens. In other words, we are talking about a stochastic background. So the idea is that how do you generate this background? Well, there are different possibilities. One of them is cosmological. So there was, as I'm going to explain, is the most relevant one. There was a kind of transition in the early universe, so very far away from you. All right, so there were some sources of gravity waves, so they are so abundant that eventually the signal that comes to you is generated by the accumulation of all these sources hitting the Earth. And this is a kind of collection of waves which is incoherent because these guys don't talk to each other. As opposed to waves, and there are many of them, as opposed to the waves which are generated close to you. This is what is called a foreground, right? Where you, in principle, can distinguish individual guys. So the idea is that we're going to take this stochastic background of incoherent and persistent waves. This is just, I already mentioned. There can be astrophysical and cosmological. So you have maybe heard about and I'm going to discuss mostly stochastic gravity wave background from early universe. But this kind of backgrounds can also be generated. You have, imagine that you have millions and millions of binaries. And this is also a kind of background that it's also discussed for LISA, for instance, where in principle, LISA will have this kind of background of many binaries, maybe too many, to really see a signal, right? But for the frequencies I'm going to discuss, this kind of astrophysical backgrounds may be supermassive black holes, because we are going to discuss low frequencies. Finally, when you talk about these backgrounds, the phase is not so important. What is really important is the energy density. So how much energy, well, how many gravity waves in amplitude get to your detector, because as I said, the phase is modeled as a Gaussian or whatever stochastic background, stochastic variable. So the relevant quantity is the energy density. And cosmologists like to write this in terms of the energy density, which is critical. Okay, this is a cosmological value, and of course, it's going to be important that you don't want the whole energy density, but the energy density at a particular frequency. So the standard, as I said, quantity for, to characterize this stochastic background is going to be the amount of energy density per unit frequency. Okay, so that's the background. So where we stand on these observations, so you may think that we are very much advanced, but we are not. Well, of course, we have amazing observations already. Well, not observations, limits for this background, but still we are very far away from kind of a spectral coverage of the gravity waves. This is today. This is a frequency in hertz. This is the amplitude of this energy density. And first, let me start with this curve here, based around 10 to the 2 hertz. This is LIGO Virgo, around 3. All right. There is no detection yet of a background, so all the events have been just single events. So that allows them to put a background which is quite, well, this number, in principle, you don't know when it's going to be relevant. Of course, you want it to be small in terms of cosmological terms, otherwise it could be dominant at some point of the history of the cosmological evolution. So in principle, it should be small, but how small? Well, of course, you want it the smallest you can. But, well, I'm going to put now a line at some point, which is the aim, psychological aim of this community. But for now, yes, LIGO gets here. There is the other nanohertz bound on the, coming from pulsar timings. So here the idea is that there is a pulsar emitting, the light's coming to you, and as it goes through from you to the pulsar, it meets these waves, gravitational waves. This changes the time of arrival and the frequency of the wave. At which scales? Well, kind of hundreds of parsecs, which eventually corresponds to these frequencies, right? So this is why, I mean, in a sense, you are seeing by these two different, but by this huge spread, you are seeing kilometer size experiment, parsec size experiment, right? So what's going to happen? Oh, sorry, other bounds at Earth size experiment, Earth in terms of the wavelength corresponding to the gravity waves of this frequency. There is also a modest, I would say, bound on gravitational waves coming, hitting the Earth, shaking it around, and because we have very good seismography, okay, you can say, okay, look, there is this, I mean, the background of gravity waves in these frequencies that are the frequencies of the normal mode of the Earth are not bigger than that. Similar, there are bounds from the orbit of Cassini, which is artificial satellite mission, basically flying around the solar system. And again, now you have larger sizes. And finally, there is some cosmological bound, which is to be taken with a grain of salt, but still is kind of the psychological barrier for this field. This is calling from an effective. So eventually, the energy density of the gravity waves you have shouldn't be dominant at BBM times, for instance, right? And that means that you cannot have a lot of this energy density, and it's typically parameterized by a line. But of course, it's not. I mean, this line corresponds to integrating all the energy, not to one frequency. You assume a power spectrum which is flat, and then you assume that then there is such a bound. But in principle, if there was a very peak distribution of energy, this bound is to be redone. Okay, so this bound is really assuming a spectrum, is model dependent. Whether these ones really are a bit less, I mean, they're really constraining the fact that you have a background which has this amplitude, and well, normally you do it with a collection of possible tilts, but these are, if you want, more model independent bounds. There's a cutoff you're assuming, but it's relatively high. So. No, not for this particular bound. Is there a problem? Okay, He was asking if of course you don't assume a fully flat spectrum, but you have to carry somewhere. This is today, and this is going to be the future. Of course, one of the reasons why we are busy with gravity waves is that there are already some ways forward which are very exciting. I mean, this is going to be the natural progress in this frequency band, the Einstein telescope, or something that, I mean, in this same idea of kilometer size interferometer gets to the best possible technological experiment. So this is this one. In the nanohertz, better radio astronomy, SKA is here the principle, the game changer. But what is really more important for the field is LISA, which is going to have millions of kilometers in the arms. So that means that you start exploring a region which is not covered at all in, at any interesting scales. So this LISA is almost approved, in the sense that if the NASA engineers agree that it's fine, it's going to be fine. But the NASA engineers, sorry, NASA, ESA, they may say, no, this is never going to fly. So some people are stressed about this. Okay, but there is also another kind of experiments based on atomic interferometers between these two guys. So this gap is kind of being covered. Well, this is super optimistic, but if you have a tower and a fountain of atoms up and down, and this kilometer size, then gravity waves going through are going to change the kind of atomic interferometry done upstairs or downstairs, and you can start filling this gap. If you ask what can these guys in atomic physics do today, they are over here. Okay, the one. I mean, this is an optimistic bound, and maybe it will happen. But then there is something maybe more relevant, is that there is a gap, okay, in the microhertz band, and the reason why this is there, in a sense, is that you need something between, let's say, galactic scale and solar system scale, where you can time well something, right? Because gravity waves are very, very subtle, so you need something in this band. So an astrophysical system which has kind of, I mean, as large, which is large and precise or sensitive to a new signal. I will discuss maybe later a bit more on the talk what was mentioned by Jens yesterday. There are other gaps lower in these frequencies, and now the question is what to do here. So this is taking me back to this idea. So the gravity waves of these wavelengths, okay, which correspond to maybe days or some days, may cause the changes in the binary evolution of systems which have days, 10 days, months, time scales. And this is going to happen, as I said, for these frequencies which are on band with these guys. And eventually, the relevant thing, as I'm going to show, is that this is not just a process which is like a random walk or a random process, but it may accumulate if you are in resonance. To be in resonance, you also profit from the fact that you have a stochastic background. So when you do the averaging and everything, there is always, in a sense, in this large amount of waves, there is always one that is going to be in resonance with you, and this means that eventually, on average, these effects may accumulate with time. It can be what is called a secular effect, right? So there are two guys oscillating, and because here I have basically all the frequencies with all the phases, eventually this guy who is oscillating is going to be in resonance with the other guy. Okay, so how do we do it? The idea is to go back to how people describe binary systems and how do they describe what happens when you have a perturbation to the binary system. So here, you take Newtonian limit in the sense that these guys, they're going to be quite non-relativistic. So Newtonian physics is kind of enough. You can add GR if you want in the post-Newtonian way, like order by order. But in principle, the systems that we explore are quite non-relativistic. For this, the way to explore perturbations to the orbit is to consider the 6 integrations of motion of the binary system. Some of them are better known than the others. So these guys are constants in the case of Newtonian dynamics. So for instance, the period of the orbit, the eccentricity. So this has to do with, you have the orbit and you put yourself, you align yourself with the orbital plane. It is characterized by the period and the eccentricity. Now there are others that have to do with the orientation of the orbit. So you have you see the orbit and there is you fix an external coordinate system. Then this orbit is oriented with some inclination and also with some declination like this. So these are these two numbers here. And you can imagine that as the orbit progresses, if it is not Newtonian and there is a kind of constant motion, it can also have this motion or this motion, right? So this is something that, again, it doesn't happen in Newtonian dynamics. It's going to happen if the orbital motion is modified by a background. Finally, there is the pericenter, okay, which is very well known because GR changes it. The mean anomaly of epoch, okay, which in a sense we can forget about it because I always get confused how to explain it. So the idea is that there are these 6 integrals of motion in the Newtonian case that become dynamical in the case of a perturbation of the orbit. And this is something that has been understood since the 1800s, because of course this is the kind of equations that, I don't know, Le Verrier or whatever were solving to try to understand the solar system. Yes.
Oh, right. There's no sound.
Yeah.
How isolated does this binary have to be for perturbations from other, if it's in a cluster or something, like quasi-like oscillations not to happen? Obviously
it depends on the kind of measurement that you are making. For what we're gonna do, we're not gonna do a final analysis. We're gonna do the following. We're gonna take a binary system. And we take the data from some people who claim that they can predict how this evolves. For instance, how does the period, which by the way is the same as the size of the orbit, how does it change with time? For instance, they will tell you, the orbital motion is understood to the level that the noise is U1. So the extra effects on the period are, it cannot change more than, I don't know, 1 centimeter in 10 years. And then we're going to put our noise on top of it. This is not a clear, then to really have a bound, we will need to now do everything together, because there may be some degeneracies. But for now, we're going to just assume that whatever was the system, there may be noise here, noise there, the astronomers tell us that they understand the level of accuracy in P at a certain level, whatever happened. And yeah, I tell you that if there is a gravitational wave background which generates a bigger effect, that's ruled out. Now, if I see this effect being exactly what I'm looking for, then I'm going to have some trouble to really say, no, guys, this is a gravity wave background instead of, I don't know, a asteroid going through or something, right? But for now, the name of the game is really put constraints. Is it clear? Yeah. As I said, this is not a new idea. Well, the idea that a binary resonance happens when gravity waves go through a binary system. This is Misner, Wheeler, Thorne. This is an exercise on, and they say a gravitational wave passes, the proper separation oscillates. I have the formula somewhere in the slides. I think I'll jump to it. But they also conclude that this is never going to be a good detector because the sensitivity or the other backgrounds are never going to be so precise that that you can pick up this effect. That was 50 years ago. It was rescued by Lamb collaborators 8 years ago, where they did the calculation for a stochastic background and pulsars, assuming also a flat background. Okay, the paper is quite nice. It's not complete to the level, I mean, that we are gonna discuss here, but they kind of got a pessimistic result because they only consider flat backgrounds, and when you consider flat backgrounds, then it's very hard to beat PTA or LIGO. So you really need to go to something which has a peak. We had a similar idea of how these dark matter models that Lam was describing yesterday that oscillate with time, right? They may also be been affecting binaries. So the idea is kind of similar. There is a binary system, and suddenly in the galactic halo, there is a frequency which is selected by the oscillations of the ultra-light dark matter. Well, also Federico is an expert on this. And the idea is that, yeah, the binary may react. It may become wider, may become smaller. It may destroy completely, right? So it was kind of time for a closer look, and I was very happy that Alex was in my institution because he's really the driving force on this. So what we did, I'm gonna jump ahead to, I had to put it, okay, yeah, because depending on time, I mentioned this or not. So the idea is that you take the binary system, all right, acceleration, and this is the Newtonian part. What I'm saying is that there is a extra piece of the relative separation coming from a gravity wave going through. And if you are in the center of mass, what is this? This is given by this curvature. Well, it should be curvature of the wave. And also it's proportional to the separation. It should be, right? Because otherwise, because the equivalence principle, you shouldn't be able to see anything. So the idea is that because these two guys see a bit of a different background of the wave, okay, they are affected by the wave. Now, if you have such a general formula, as I said, this general formula is the same formula that people have been using to solve the Moon-Earth system since the 1800s. And what they put here are all the possible perturbations from the solar system, whatever. That means that they have been general enough to make us really, I mean, take the formalism blindly and just move forward. So what you do is you take this acceleration, this x acceleration, and you decompose it into the radial motion of the orbital motion, the angular motion, and the perpendicular one. So the orbit has like radial vector, angular, and then this is, if you want the angular momentum direction. You decompose this in these three directions, and from these three, FR, F theta, whatever, you now can find how the orbital parameters change as a function of time. This is, as I said, this is in the books of orbital dynamics. For instance, if you take GR corrections, this is a given term, the post-Newtonian correction, what you're going to find is that this is whatever, because the perihelion advance. So this is another way to do the, if you want, a highbrow way to do perihelion advance in your GR module, to do it with this osculating orbits is called. But this is more powerful because this will describe all these possible fluctuations. Now, if you put the gravitational wave signal in, these guys generate oscillating, this is going to oscillate, right? The curvature oscillates. You're going to generate oscillating FR, F theta, and FL. So for instance, take the period, this oscillates with time. And if the orbit is not totally circular, some of these guys in principle also oscillate with time. There should be a radius somewhere. Yeah. So in principle, those are not exactly time independent variables. So that means that they generate a kind of resonant effect when you average in time. Because there is one, no, this is time dependent. What is time dependent in this case is this guy, this phi. This time dependent and is has the frequency of the period. So the frequency of the binary. This has the frequency of the wave. When you take a time average, that two cosinus, if those guys are on resonance, so this accumulates with time. So P grows with time or goes down with time, and the same with the rest. All right. So this is the, as I said, a kind of the exercise we had to do was to compute FR, and then this is kind of straightforward. Now I go back, I think. Yeah.
So here the assumption is that this is still a periodic perturber, right? So it's a background which basically doesn't change, but it's just doing a period.
Yeah,
periodical.
That's why you need well, you could also do it with a constant omega, but having a stochastic background is even better because there will always be.
But I mean, when you do the Ausculting orbit treatment, you're normally, you really need basically a periodic perturber. If you have something that is more like a pulse, in some sense, can you be sensitive to that, and can you treat it this way as well? Or?
I think you can, because in principle, well, I mean, this in principle, this can translate in something that also modifies the orbit as the orbit progresses. But it's true that we have not computed. This normally is done for many evolutions of the orbit, where, as I think what you have in mind is that you change a little bit the orbital, so you're always close to an orbital motion, and you describe it, I mean, as a small perturbation, and that's the right way to do it. Now, the difference with precisely with other formalisms is that, what is this guy? Well, this guy is going to be a kind of random motion, right? Because this is a stochastic background of gravity waves, so this is really, you take this as an stochastic signal. That means that what you have here is a kind of Langevin equation, where there is a noise term. Okay, this is the noise term, and this is, you want a deterministic piece. So the way we treat it in our paper is precisely in this way. So this is a Langevin equation with a noise term, and it's gonna change with time the stochastic properties of the parameters of the binary system. So in principle, these parameters are very localized, so they are really deterministic. As the background hits the evolution, is like a random walk depending on what you see. What is this gravity wave that you don't know? And eventually, the best way to describe this is with these Fokker-Planck equations, right? I don't know if you are so familiar with that, but the idea is that you have a system that evolves like this, like there is some acceleration or something, and it has some deterministic piece and some noise part, and eventually, a good way to describe this system is in terms of the PDF or the stochastic properties of the variables of interest. So this omega is, there is a way to go from the Langevin equation to a description of the probability distribution of the orbital parameters in terms of two different parameters, which are called the drift and the, I forgot it, but I have it in a slide, I think so, and the diffusion coefficient, sorry, that eventually, as I said, you start with a period which is kind of a fixed variable, but because it's been constantly hit by a random noise, it kind of fluctuates, right? And this is described by these two guys. So given the Langevin equation, there is a way to compute these two components, and eventually there is a way if you want to describe how the evolution of the orbital parameters is evolving. And I go back to my main text. All right. So in words, imagine again that you have a distribution of the period, which has a very fixed value. The period, right, is almost a delta function around the value that is fixed by the deterministic evolution. Now, the drift part of the Fokker-Planck is moving the mean value in one direction. So it's really, if you want this stochastic motion accumulates and drifts the parameters. And there is also the diffusion part, that what it does is that as a distribution, it makes it wider. So when you see the data is going to have this, as you want, it's like a noise, an intrinsic noise of the data. Okay. So to compute this, it takes some effort. This is not easy, in the sense that you have to really take the equations for the random noise in this case, which are non-trivial, and go and compute these two guys. But okay, we did it, and eventually, as expected, both the drift and the diffusion terms depend on the source of gravity waves at the frequencies which are resonant with the period of the binary system, right? And there are some coefficients here, and the larger the n, the smaller the coefficient. So you tend to resonate with the first one or two of these infinite series of resonances. Cool. So this is the mathematics. And now, well, why we can do this? It wasn't done already in the 50s. Is because we have at least two incredible systems where we have very accurate, very precise determination of the orbital motion. One of them is binary pulsars, in which, well, you can have here there are two pulsars, but it's enough there is one pulsar orbiting another star. They are quite isolated in the sky, and more importantly, the orbital motion is understood to very precise level. And one of the reasons is that the pulsar emits radio waves along a direction, and as these radio waves are in line with our detectors, that allows us to track very well the motion of the pulsar guy, and eventually have a very good understanding of the orbital motion. So this is one of the things that in the 60s no one could imagine we could do. Another one is the lunar and satellite laser ranging. Let's take the moon. And in the moon, there are some mirrors that have been monitored since the Apollo missions, that eventually you can say that, okay, the Earth-Moon system is very dirty. How come you can do anything with precision? But the idea is that I don't care. They have a model that tells me that the average noise on the distance to the moon is around centimeter. Okay, in 30 years, they have a model tracking the moon up and down. There's a lot of noise. This the signal goes there, comes back. There is atmosphere, satellites, whatever. But eventually, the model they have is precise enough to the centimeter level over 30 years. So that means that over 30 years, nothing has changed the orbit. Nothing that they don't understand has changed the orbit more than 3 centimeters or whatever, right? So that's what we are doing. Of course, in our mind, what we have to do is to take the data, put the new extra source of noise, and see what happens, right? Because maybe eventually, but for now, let's be optimistic, okay? And being realistically optimistic or optimistically realistic, we get these bounds, which are quite good, I think. So the solid lines are today bounds, but not bounds, projected bounds, as you want. And dashed lines are what we think is going to happen in the 38. So for binary pulsars, we have a broad coverage because we have many binary pulsars. And in principle, by studying them and the different frequencies that kind of can resonate, you can have an envelope on these frequencies, which is quite broad and also quite okay today. So you can achieve 10 to the minus 2 as compared to the other bound by Cassini, okay, with no cost, no mission, nothing. We can already start to cover a new region. The more interesting bits are these two well-picked guys. One of them is the Earth-Moon system, which is basically at the month frequencies. And this one is a satellite, which is the best one being tracked today, which already today kind of hits the ineffective bound. So that's quite impressive. In the future, you take the SKA specifications and you monitor these pulsars well enough, it's very interesting that you are going to hit the ineffective line and even get better. If the guys doing the lunar laser ranging get their money, they can go back to the moon, change their mirrors, and then eventually, taking what it can be done today, one can really reach an amazing precision here. Okay. The reason why this is not exactly a line is because, as I said, there are different resonances you can use for this line, and eventually the envelope is not just a line. There's a kind of there's a kind of you can play a bit with this frequency band. This has to be compared with the rest, and also you want with the ineffective line that is going to be this one in this 38. So that's the main message of this method. And now the question you can ask, and also the question that you can ask to Jens, is who cares? Because everyone now is having gravitational wave backgrounds, which exactly are either in the LISA band or in the PTA band. Well, this is just biased by what people can detect. So you take, for instance, different backgrounds, and you start playing with the parameters. You can start filling up this parameter space with backgrounds. So this is, for instance, a first order phase transition that I will discuss, which is not seen by PTA, is not seen by LISA. It's quite huge in the sense that it goes above ineffective, but being a peak distribution, this bound is to be redone and it's basically inexistent. And the moon already picks it. Okay. Maybe more importantly, the nanograph anomaly. So nanograph is a PTA observatory, and it has already observed a signal somewhere around here in the nanohertz. It's not clear whether this is, thank you. It's not clear whether those are gravitational waves, but if they are, they can correspond to different backgrounds with different spectra. The one which is maybe more astrophysically relevant is if those guys correspond to supermassive black hole binaries. And in this case, the expectation is that the background goes up. And if this keeps going up until these frequencies, the next maybe the future observations of the moon would confirm it. I think that would be incredible if you can see this in these two experiments. Otherwise, well, nanograph is strong enough in the sense that the good thing about these guys is that they can really see the spin-2 nature of the waves. So if they manage to see it, then they don't need much complementarity, because that will already be a discovery of gravity waves in this band. But for now, this is not possible. So they have not been able to detect the spin-2 nature of the signal. There's a signal. I think everyone agrees with that. It's not clear whether those are gravity waves. All right. Now you can even become more exotic and think about other backgrounds. For instance, this one I'm not going to discuss, but let me discuss these green lines, which unfortunately don't reach us. So those are what are called super radiant clouds of supermassive black holes. So you have a black hole spinning, and if the dark matter has a mass which is in a sense also resonant with the with the spinning frequency of the black hole, it generates around the black hole a cloud, okay, of the dark matter. And as it spins, this cloud has a very, very big moment of inertia, which is moving. So it generates gravitational waves, which are almost monochromatic, right? And the frequency has to do with the mass of with the spinning of the gravitation of the black hole. But to generate the cloud, the spinning and the mass of the dark matter candidate have to be related. And if you take what people expect for these black holes to be emitting for different dark matter masses, this is for 10 to the minus 21, 10 to the minus 20, 10 to the minus 19, 10 to the minus 18. They also generate peaks, okay, that we are unlucky that we don't see. That, for instance, are things that maybe only LISA will see, for instance, or maybe only aliens will see. So there are also these kind of backgrounds that pick whatever you want, in a sense. And then for us, the most relevant ones are the first order phase transitions from the dark sector. So let me just, in my last 5 minutes, mention them a bit more. So they are a key prediction for many particle physics beyond the standard model. So in particular, because of LISA, many people are now trying to cook up models of early universe where you have phase transitions around you and they generate enough gravitational waves and at the frequencies which are around 10 to the minus 2, 10 to the minus 3 hertz. But this peak, where it is, how strong it is, in principle depends on 4 parameters: the temperature of the transition, the something called the strength, the rate as compared to the Hubble rate at the time of the transition, and again something called the bubble wall velocities. And when you take order 1 values, well, or expected values for these guys, the relevant thing is that the temperature of the transition is like 100 GeV, which is a very natural energy scale for particle physics. Then the peak of this gravity wave spectrum is around the microhertz, so around the frequencies I am talking about. So in principle, for LISA, people are playing with T to make it a bit higher to make this peak what they want. Yeah, but if you take 100 GeV, this peak is where I want. And if you make it even smaller, you can go to also below PTA. So in principle, there is some game here of which phase transitions you prefer. We did an MCMC analysis of which phase transitions are going to be visible by us. Let's take lunar laser ranging, blue. Which ones are going to be visible by LISA, SKA, and then we compare with an effective bounds. Of course, if LISA flies, or where LISA flies, it's very hard to beat it, because in a sense you have to fit the transition exactly here. If you change a bit the parameters, then LISA starts to be seeing it, or PTA, SKA starts to be seeing it. But still, there's a whole collection of of models which without any particular mission that we have to do, because no one is going to go to the moon to do this for us. So if they do it, they will do it themselves. We can, constrain, for instance, let's say the energy scale of the transition is in blue. This is the rate. There are some parameters that only we can constrain. If you forget about LISA or SKA, we will be the only guys in this game. So I think it was in a sense unexpected or expected. I don't know. It was a very nice result of this exercise, that already with the Earth-Moon system, if you improve a bit the mirrors, you will be able to constrain this early universe dynamics. Yes, before I finish, there is another gap mentioned by Jens yesterday. So this is your paper. I put here the one I found from the Gaia guys. So, well, there is a gap between nanohertz and cosmological scales. And Jens was saying that you can try to cover it with spectral distortions. I am now thinking that maybe the hitting of binaries, white binaries so you need something which has long periods now. So maybe the hitting of white binaries on the Milky Way may also put about, I don't know. And I think you are almost at the same value, because this is omega h squared. Here there is no h. So h squared is going to put this bar down to 10 to the minus 4. So I think that is almost the same. But okay. So here what they do with Gaia is really they look at the position of the stars with the precision, and then the angular, the tilting, if you want, of the stars in the field.
Oh. Is it a bound that is really integrating the full scales, or is it what are the bin sizes in this?
I don't know.
Because for the fibers case, this is still binned, right?
This is bin. I would say
this is more like a let's say delta function approximation. So
I think this is an integrated bound.
Yeah. So like the ineffective bound. The ineffective bound is a full integral, therefore very strong. If you made it a bin, you would have no constraint almost. Right? So just to put it in perspective, yeah.
But it's okay. Come on, you are still stronger. Yeah. Okay. But there is this other gap, and as also was mentioned, I don't know which kind of backgrounds. So there are two ways of thinking about these gaps. One of them is if there is a background which is flat, and you reach it by different or with some spectrum, and you reach it with different observations. That's the only way I think people are going to believe you. And but also there may be phase transitions with the energy so low or whatever that, or with parameters which I don't know what they are, that they can fit here. Okay. And I'm gonna finish here. Yeah, this is my summary. I think I already mentioned everything, so thank you very much.
So Diego, thanks a lot for this very nice talk. So are there more questions in the audience? I don't, okay, please.
So I just have a question about the Earth-Moon system. So do you kind of know what are the levels of the degeneracies with the tidal effects and things like that, or is there any chance? Because it seems like it's a very dirty system. Like there's a moon is drifting away from the Earth and so on gradually.
Yeah, but normally, if you think about all these terrestrial scales, they are not on phase with the. You want, yeah. Well, you have to imagine that all these tides or these other periodic gradient noise or whatever which is around us is not very much excited in the month scale. So in principle, we may be safe from this point of view, but I don't know. There may be something which exactly varies with month scale that maybe. You want the optimistic view is that you take these are the bounds coming from the normal modes of the Earth. So I assume that this is the kind of frequencies that are natural for the Earth to ring on. So in principle, you can, I mean, they happen at frequencies which are much higher than the ones of the moon.
Thanks.
Yeah, but I agree that now our effort is really to do a real analysis. We emailed the lunar laser people, they didn't answer. I emailed to 10 people, they don't care. Okay, they have their own agenda, I guess.
Are there any further questions in the audience? Okay, let's check whether there are any questions on Slack or Zoom. Is there anything? No. Okay, then let's thank Diego again for this very nice talk.